Good afternoon, everybody. So I'm going to have a seminar or discussion on exhausting solid dispersions, what we have done in our laboratory and what we have observed is the enhancement of solubility and permeability. So the content includes a general introduction, then objective of this study, the materials and methods, results and discussion, conclusion. So in fact, this exemestane is an orally active, irreversible aromatase inhibitor, a steroidal drug, which is used in the treatment of post-menopausal women, generally in the breast cancer. But however, this exemestane has been observed to have a very low aqueous solubility, that is around 80 microgram per ml, and which has been leading to the poor dissolution and also incomplete oral absorption. So thus the enhanced dissolution of this exemestane is an important concern for enhancing its viability as well as its therapeutic efficiency. So in this study we have planned with the simple solid dispersions using the most widely used polyethylene glycols as a carrier because of its low toxicity, that is the low melting point of polyethylene glycols and also rapid solidification rate and low cost effective, and actually already proved as a physiologically tolerable component. So the materials, as I said, involves the exemestane, the active ingredient, and polyethylene glycol 6000 and 20,000 and other solvents. So the methodology includes the first conduct of the phase solubility studies to first understand out of the two carriers, PEG 6000 and PEG 20,000, what we have studied, which is having a better solubility profile. So in this regard, we have conducted this phase solubility studies using this already reported Ibuchi-Konos method, which is an excess amount of exemestane was placed in this aqueous solutions of PEGs of 6000 and 20,000 at various concentrations ranging from around 5 to 30% in a glass wall, and it's been shaken for 48 hours, and the samples were filtered and measured for the exemestane content by using HPLC analysis. And these phase solubility diagrams were plotted to carrier concentration against the soluble exemestane concentration for understanding the profile. And this was the HPLC analytical method what we have used, the mobile phase constituting methanol in water in 80 to 20 parts and flow rate of 1 ml per minute at UV detection of 250 nanometers, injection volume of 20 microliters. Then after conducting the phase solubility studies, out of which we have seen the 6000 has shown a better solubility profile with a linear increase, out of which we have taken the PEG 6000 as a carrier to make the solid dispersions, and solid dispersions were prepared at a concentrations of 1:1, 1:5 and 1:9 by the solvent evaporation method, and higher concentration of 1:9 physical mixture was prepared by simple mixing in a glass mortar, and all the samples obtained were passed through the 60 mesh screen or 250 mm CU, and the product obtained was stored in a desiccator. So then the solubility, saturation solubility of these components or the product obtained was studied by taking excess quantities of each preparation in a glass vial, so 10 ml of distilled water to understand the solubility improvement after preparing the solid dispersions and physical mixture. And similarly, the exemestane content was estimated using simple HPLC analysis. So further, the solid dispersions obtained were solid and understood for the solid state characterization using DSC, differential scanning calorimetry. And the samples studied were pure exemestane and pure polyethylene glycol 6000 and 1:9 ratio of solid dispersion, and its respect to physical mixture, that is 1:9 ratio of physical mixture. So the DSC analysis was carried out at a scanning range between 30 degrees centigrade to 300 degrees centigrade at 10 degrees centigrade per minute. And then XRD studies were conducted by using XRD refractometer or a range of 3 to 50 2-theta values, and the degree of crystallinity was obtained with a simple formula, that is intensity of SD by intensity of drug, that is ISD is the peak height of solid dispersions or respect to physical mixture under investigation with respect to the pure drug peak to understand the degree of crystallinity in the pure exemestane, then followed by the solid dispersion and physical mixture. The scanning electron microscopy figures or scanning electron micrographs were taken to understand the morphological information of these formed solid dispersions and pure drug. And finally, the enhanced dissolution or the dissolution characteristics was carried out by using the electrolyte USB type 2 apparatus at 50 RPM, and dissolution media studied was distilled water and also 0.1% SLS in distilled water with 900 ml volume and temperature maintained at 37 plus or minus 0.5 degrees centigrade, and aliquots of 5 ml were collected at predetermined time intervals over a range of 2 hours, and the samples were analyzed by HPLC. And further, to understand the improvement of permeability, the in situ permeability studies were conducted by single pass intestinal perfusion studies, which has been done as per earlier reported methods. And so after the anesthesia of by intraperitoneal administration, and midline abdominal incision was made, and 10 cm section of the proximal right jejunum was located gently with the plastic tubing and attached to the perfusion assembly, which consisted of a syringe pump, and a 20 ml of syringe was connected to it. So the outlet tubing was placed around 10 to 15 centimeters above to the first opening, and blank perfusion was made with the same phosphate buffer saline, PS 7.4, was infused for 15 minutes by syringe pump, followed by perfusion of compounds, that is the pure exemastine, and also the 1:9 ratio of solid dispersion was studied. And samples were made every 15 minutes for 90 minutes of time. And the samples obtained were analyzed by using HPLC. So the steady state intestinal effective permeability was calculated using the equation, and where Qn is the flow rate of perfusate, that is, which is generally maintained at 0.2 ml per minute in the study, and A is the surface area of the intestine segment, which is assumed to be area of cylinder, that is 2 pi RL, and based on that the area was calculated, and the radius was 0.18 centimeters, and C in and C out or the inlet and fluid transport corrected outlet solution concentrations respectively. So coming to the results, as I said, the phase solubility studies of PEG 6000 and PEG 20,000 was carried out of which PEG 6000 showed a very good linear relationship, showing the AL type curve when compared with the 20,000. And if you can see the data here, the concentration of exemastine at 30% concentration was around 0.5 to 9 mg per ml when it compared to 0%, that is 0.077 mg per ml. So R square value or the linearity was better with the PEG 6000, and its stability constant was 183. So this suggests the formation of a better complex within these ratios when compared with PEG 20,000. And it is been reported that the stability constant value within 100 to 1000 facilitates a better complex, and more than that a very strong complex, and below 100 it suggests a very weak complex. So out of the two carrier studies, 8000 was further, 6000 was further carried out with solid dispersions, and saturation solubility studies showed, as we see here, the solid dispersion 1:9 ratio showed an improved solubility, and the differential scanning calorimetry for solid state characterization suggests that the drug peak was there in the A, that is figure A, and when you see with the B, C and D, so B is a pure exemastine and C is a exemastine PEG physical mixture, and also D is a exemastine PEG 6000 solid dispersions, all of which we could not find this in a solid dispersion, suggests that it will transform P. So the degree of crystallinity was understood with the X-ray diffractometer, and the A was a pure exemastine which shows some crystalline nature, and B was PEG 6000 with 2 probable peaks, and physical mixture with 2 peaks of PEG along with some peaks, and whereas in the solid dispersion, that is at D, we could not observe that, and the degree of crystallinity was observed to be decreased when I compare with pure drug. It is around 5104.33 to solid dispersion 439.3 at a 16 theta position, and the same case with the 18 theta position, it is also relatively reduced. So the degree of crystallinity was reduced tremendously in the solid dispersion 1:9 when compared with the physical mix. The scanning electron microscope also suggests the formation of complex, smooth surface complex, as we see with that of PEG. when we compare with the pure drug. And the dissolution study of this solid dispersion suggested as the improved dissolution rate of the solid dispersions in 1:9 ratio when we compare with the 1:9 ratio of physical mixture, and also solid dispersion 1:1 and 1:5. The same profile was observed in the medium, that is 0.5% SLS in distilled water. The similar dissolution rate was increased in 1:9 ratio. So this was further studied in understanding the permeability study, and this was the data for the dissolution, understanding the dissolution parameters, that is Q50, that is amount of drug released in 15 minutes, and Q60, that is at 1 hour, and dissolution efficiency at the same 15 and 60 minutes of time, mean dissolution time. So we suggest the decrease in MDT indicates the increased dissolution rate. Similarly, the dissolution efficiency values also suggest the increased dissolution rate with the solid dispersions 1:9. The same case with these ideas, that is initial dissolution rate values. So the in situ permeability studies also showed that pure hexamastine has showed a decreased permeability when it compared with the solid dispersions of hexamastine. That is effective permeability coefficient values of hexamastine and hexamastine polyglycol solid dispersion using this single pass intestinal perfusion studies. So this shows that improved permeability as well as solubility with this solid dispersion. So the solid dispersions of hexamastine with polyglycol 6000 showed enhanced solubility and dissolution rate, and also they exhibited enhanced permeability in this in situ studies. So however, this further it has to be confirmed by carrying the studies in vivo animal models, so that we are planning to proceed with. Thank you. Thank you for giving me this opportunity.
First of all, a very nice presentation. Discusses the science very well. When you have done the percentage crystallinity measurements, can you please go back to that slide when you showed the Yes, please go back to the previous slide. So when you are using the peak at 16 theta 2 theta position and the 18.17, essentially you are assuming that the crystalline form is getting converted to the amorphous form, and that there is no other morph transformation which is taking place. Am I correct?
Sir.
So have you validated that no other morph transformation is taking place by doing any additional experiments?
No, sir. This is the only experiment what we have done to understand the transformation of crystalline nature to amorphous form. With this, we have seen, and the same case with the surface, same pictures also suggest that this crystals of pure drug is not present on the solid dispersions.
Do you also have access to Raman spectroscopy at your facility?
No, sir.
Okay, maybe you want to think of trying some of that also, because a lot of cases whenever you do this, there is a small but finite possibility that morph transformation would also be taking place. And whenever you draw these conclusions, most people would ask you to rule out that possibility. Okay, thank you.
Thank you.
Questions? Thank you. Thank you for coming. Now, can I call upon stage Professor Sinrick, RAPT, to felicite Dr. Bandari.